Who are you and what do we need to know?
My name is Adam Rogers. I wrote a book called Full Spectrum: How the Science of Color Made Us Modern. And the basic premise of the book is that there is some fundamental science and technology behind the ways humans both see and then make colors, and that the pursuit of that science and technology has been one of the shaping forces around human history.
In 2015, you wrote an article that was read by 38 million people across the world. That article focused on the many subjects covered in this book. Could you talk of that article?
Sure, that was an article about the dress, which we usually write with a capital D and sometimes a capital T, also depending on the house style of the copy desk that's publishing the article. You might remember this. There was a meme on the internet where people looked at a picture of a dress, of a woman wearing a dress, and assorted themselves into two groups. Some people saw that dress as being white with brown trim, and other people saw it as being blue with black trim. And that doesn't seem like that big a deal, but people so adhered to the way they saw that dress that it became like the red and blue divisions in the United States. It became like it was like the War of the Roses with colors. It was astonishing the degree to which people both once they saw it stuck to that belief, and then thought that anybody who saw it the other way was nuts, was just crazy. And this was when people were still using the internet for real stupid stuff instead of like overthrowing governments and things. And so in my newsroom, I'm a writer. I've been an editor and a writer at Wired in the U.S. for a long time, and in our newsroom, it became very clear, almost immediately to us, that was a science story. And I had spent before I came to Wired, even in the early 2000s, I'd spent a year at MIT, Massachusetts Institute of Technology, as a journalism fellow there. And one of the things that I looked at was the science of color, of how color worked both in the world around us, the photons or wavelengths bouncing off of surfaces and then coming into our eyes, interacting with receptors at the back of our eyeballs, and then getting shaped into a perception of color in our brains. And I spent about a year reading about that for reasons we can talk about. And so I had some people to call. And so I wrote this article that tried to explain why it would be possible that something that we might, as humans, intuit was an objective facet of the world, was a philosophical qualia, which is to say objects have colors, things have colors, and then we perceive them. Why that, in fact, is a really complicated and almost provocative thing to say, and to try to explain why different people would see the same thing as having different colors. And that became one of the foundational tenets of the book, is that color is an interaction really between our physiology and our neuropsychology and the basic chemistry and physics of the world.
Could you explain a little bit more about why people saw and perceived a different color? A neuroscientist called Anya Hulbert talks of this incident and says that we learned from it how differently human brains work, as well as we learned how different we all are from it. Could you go into the science of that?
Sure, it did. This was in as much as the picture of the dress kind of shook up the internet for a day, it really shook up the people who study color and the perception of color in the brain, because it called into question a lot of fundamental things that they thought they understood, and it turned out that they didn't, or at least they didn't understand all of it. So one of the things that our brains do for us is a principle called color constancy. And what that is like we essentially subtract the color of the light shining onto something from the color of the object. So here's an example. If you see a picture of an egg, like an egg that we would eat under red light, our brains don't tell us, oh my gosh, it's a red egg. Our brains basically say like, well, that's an egg and there's obviously red light on it. And nobody's really sure how we do that. It might be because we we remember what color eggs are in our brains. It might be because we compare the color that we're seeing in front of us to the color of something familiar. There's a lot of hypotheses about how this works. But what happened with the dress was essentially a failure of color constancy in a very specific way. And the theory is that one of the ways that people evaluate the color of something is by taking a very good educated guess as to what color the daylight is on it. And we're very familiar with, there are a bunch of maps of all the colors that a human being can see, or all the colors that exist. One of those maps is sort of a horseshoe shaped thing. It's put out by the French standard setting organization that works with colors. But there's a specific axis across this map of colors called the daylight axis. And it's the colors that you would think of as being the kind of early morning, sort of early morning pinkish to midday clear, bright white to late in the afternoon, kind of bluish indigo, and then the colors of sunset. And when people looked at the picture of the dress, their brains, this is the going hypothesis, our brains made an assumption as to what time of day it was, and said, well, if you were the kind of person, for whatever reason, maybe because you're a nighttime person who stays up all night and doesn't like being awake in the day, or vice versa, if you thought that it was a picture of a dress in shadow late in the day when the sun was low, then you thought, oh, well, the color of that light was sort of darkish, shaded blue, and so that's the color of the light shining on it, and you thought the dress was white. If you thought that the picture was taken, and the reason that you might get confused is the way the light kind of looked in the background. It wasn't a professional picture, it was just somebody who shot an image on their phone. If you thought that it was clear, bright, white, midday sunlight shining on that dress, then you thought that the dress was the thing conveying the sense of blue, and the light was white. And our brains, when presented with that chromatic illusion, with an illusion of color, sorted immediately into a sort of biphasic distribution. We chose one or the other. At least that's what happened initially with the dress. Some later subsequent studies said that didn't happen at all.
So the brain eliminates chromatic bias.
Essentially, yeah. And you can think about this if you've ever messed around with digital cameras. The thing about white balance, where you have to tell the camera, especially video cameras do this, where you have to tell the camera, okay, I want you to pretend this is white. Whatever thing I'm showing you, pretend that's white, and adjust all the other colors you're seeing to that. And so our brains do something similar. We take a sort of standard, we set a standard for what the color of the world around us is, and then we assume every color exists in that context. Because of course what we're seeing is an illuminated world lit by more than a sextillion photons every second hitting every square meter of the daylit part of the planet, and bouncing off of, or sometimes bouncing through and then bouncing off of those surfaces and then coming back into our eye. And so there's an interaction that happens outside our brains that our brains then have to make sense of. And in this case, our brains didn't make sense of it at all, partially because we were seeing stuff on a screen most of the time instead of as flat color around us. So the screen was emitting color instead of just reflecting those colors. And because we're not really that good sometimes at seeing those daylight biases. The really weird thing about it too was that you've probably seen illusions of form, illusions of shape, the pictures of it's a picture of it looks like a cube, but is it projecting forward of the page that you're looking at, or is it dug backwards, or is it a duck or a rabbit? Those kind of those silly little illusions that show that our brain processes information in sort of weird, unexpected ways. But with those illusions of form, our brains tend to switch back and forth. You tend to see the duck or the rabbit, or the duck or the rabbit back and forth. With these illusions of color, apparently we don't. We see the illusion and then our brains just fix into it. And so trying to understand why that was really did take a lot of the time and effort of people studying that dress, including Anya Hurlbert, who later actually got the dress, the actual dress, the real thing, and set it up, did these demonstrations and displays of it, where she would put it in a gallery and light it cleverly with LED light, so she could very carefully control what actual light was illuminating the dress. So it would look like it was white light, but it wasn't. It was what's called a metamer. It's a color of light that our eyes see as being one color, even if it's not a pure wavelength. And by tuning those lights, she could make people see that dress almost any color she wanted, not just white or blue, but a whole bunch of others. And people tend to report other colors too. And when you ask these scientists, as I would ask them sort of at the end of our conversations, but so what color is it really though? Come on though. I mean, it's got a real color. What color is it really? And they would just sort of say, oh, you sweet, poor, naive boy, You know, you just have no, there's no, you can call it whatever you want. There's no such thing as color, really. It all gets assembled in our brains, which is a concept that when you internalize it will make it so you just can't sleep at night.
In describing colour, it also goes into the realm of linguistics. There was an interesting study done by Paul Kay and Brent Berlin. Could you talk a little bit about that and the significance of it?
Yeah, Berlin and Kay's work has been foundational, and this is an interesting issue because in linguistics, in a lot of cases, the linguists, especially the foundational ones, are using color as a tool to understand language, and then the more they understand the language, it turns out they can use that to understand color. So there's this really interesting back and forth dynamic that exists even before Berlin and Kay's work. Before he became a British Prime Minister, Gladstone wrote a book that was a translation of the works of Homer. And one of the things that he said in it was he had trouble figuring out how Homer was using color terms. So there's the famous example of the wine dark sea. It's something that comes up a lot in the Homeric epics, the Odyssey and the Iliad. And he sort of said, I don't know what that means. Like, I don't know what color word he's using there. The seas don't look like wine. They're not dark. I don't get it. And that led to some speculation that the like German Romantic poets and philosophers of later centuries started to think, well, maybe the ancient Greeks actually couldn't see the color blue. This is one of the basic, like one of the ways the way our eyes perceive color is if you have color normal vision, we see these sort of wide swaths of color organized by specific kinds of receptors in our eyes, but they're organized around essentially the colors blue, green, and red. So the idea that early Greeks were somehow different than later humans is a shocking one, but it wasn't so much the idea that their physiology was different, perhaps, but like somehow that culturally they weren't able to see blue. But the question then became, well, maybe it was just that they didn't have a word for it, and that led into a line of thought in linguistics that has come to be called linguistic relativism, and it's really most associated with a sort of self-taught linguist named Benjamin Whorf, but the Sapir-Whorf hypothesis is that if you don't have a word for something, that you can't really think of it. And this has been hotly argued in philosophy and in linguistics for decades, if not centuries. The philosopher David Hume asked about it, whether people could conceive of an idea that they had never seen before, for example. And he used color too. His example was a missing shade of blue, was that if you showed a person an array of blue from light to dark, a bunch of different blue shades, and had one missing, could they imagine the one that wasn't there if they'd never seen it before? His conclusion was, unlike almost any other kind of concept, the color was a sort of special case, that yes, people could conceive of a shade of blue they'd never seen before. So Berlin and Kay were linguists who both realized that in the languages that they studied, they were both native English speakers, but they were studying other languages too, and they were having an easier time learning some of these other languages, partially because they had fewer what are called basic color terms. So you and I might talk about colors like turquoise or indigo or orange. Orange isn't a great example, but I'll go back to why. But those are all descriptions of objects that have a particular color. So if we talk about gold, for example, if we talk about the color of the earrings that you're wearing, we're talking about the material almost, and using that as a proxy to say what color it is. But there are words like in English, blue or red or yellow, that are only about the color themselves. The only metaphor that they have is for the color. They don't mean anything else. So we call those basic color terms. And Berlin and Kay wanted to understand why some languages had different numbers of those words and why in which languages. So they did a bunch of studies where they interviewed people who were first bilingual with English and then other languages, and then eventually native speakers who weren't bilingual, and essentially showed them a card with a bunch of colors on it and sort of said, okay, what's that? What do you call that one? And if they had a word, and looked at whether they had a word for it or didn't. And what they thought they found was a pattern, which was that as languages evolved and developed, and that's a pretty fraught way to put this, it has some racial implications too, but that first languages started with black and white, and then if they had another color term, it would be red. And then if they had another color term, it would probably be in the blue or purple or green world, and then it would be purple, and then. And they thought that every language evolved in that certain order. And that idea came in for a lot of criticism immediately, because people said, for example, they'd only interviewed folks who were bilingual, so they also spoke English, and what does it mean to say a language is evolving or developed? Does it mean it's older? Are some languages somehow better than others? Of course they aren't. They just have to function as ways that communicate. And it also led to a bunch of evolutionary, sort of pseudo-evolutionary questions, like, well, why do people need to see colors? Why do we have words for some things and others? So you've probably heard of hypotheses like, oh, well, you have to be able to see the color of ripe fruit against the green background of a forest, or, oh, there's an evolutionary advantage conferred by being able to infer emotional state of a person you're talking to based on whether they're blushing or not. All these things are the sort of just so stories that evolutionary psychologists tell or used to tell each other, and there's not great evidence for most of them. But what Berlin and Kay eventually did is send informants out to a bunch of different countries, to a bunch of different people in the places that they lived, interview them in their own languages. And what they found is that basically languages would have words for light and dark colors, and then they would sort of add to them based on a feature that there are a lot of definitions for this word, based on salience, based on what colors they needed to be able to talk about in their everyday language. And but this idea that if you don't have a word for something, then you can't think about it, still persists in linguistics, of course. It's probably not true, because later studies will have shown that you can show people the same array of colors, and even if they don't have a word for it, they'll recognize a difference. Sometimes they'll have different words for it, even if they live right next door to each other. There are some edge cases here. So one of my favorite examples of this is that in English, we have one basic color term for blue. Russian has two basic color terms for blue. There's one for light blue and one for dark blue. I won't pronounce them right, but it's sini and goluboy. And if you do, so there's this experiment, I love this test, where researchers showed both Russian native speakers and English native speakers what's called a triangle test. You show two examples of one thing and then one example of another. And so they would show them two examples of one of the blues, either light blue or dark blue. And then they would bring in a third, and the volunteer had to say whether it was the same or different as the two that they already saw. Russian native speakers could do that faster than English speakers. And the idea being, well, if your brain is built, it has developed with the idea of two basic color terms for blue instead of one, that somehow you're more receptive, faster, you can see blues more quickly than somebody who hasn't. Fascinating implication. I think more recent work suggests that, in fact, within normal variation, people who have normal color vision all see sort of the same range of colors. Sometimes they have words for them, sometimes they don't. In the same way that when you sniff a glass of wine, I wrote a book about science of booze too, and when you sniff a glass of wine, probably you and I are smelling the same glass. We're smelling the same glass of wine, of course, and can detect the same things. But if we have words for it, like, oh, notes of blackberry and dried fruit and leather and slate or whatever, the sommelier has more of those words, and therefore can be more descriptive of the glass of wine. Similarly, you might have more words for those colors. There's some more recent work that I like quite a lot. One of the authors is a researcher named Bevel Conway. He's at the National Institutes of Health here in the US, who's sort of like a guru for me on this stuff. And his work kind of tried to reproduce what Berlin and Kay had done, but using information theory to try to figure out, well, how many words does it take somebody in a given language to tell me which color chip to pick up? If we play a game where I say, like, okay, here's the color chip that I want you to pick up, and I describe it using any word I can, they found that what an artist would call warmer colors, so the reds, the oranges, the yellows, kind of were easier to describe, had more information contained in them. And so that's a pretty interesting difference too, that is a kind of different way, a different slice of the same problem, to try to figure out, well, what does salience mean? What is it? Which colors are more important to which cultures and why?
Can we talk about the physicality of colors and how we as humans have created all these different colors through history, and how that has been related to the discovery of new elements? If you could start with maybe talking a little of Sir Isaac Newton's discoveries in this area.
Sure, I will. I will say I did a thing. One of the things I wanted to try to do in the book was in some ways not start with Isaac Newton, only because so many color books do, and his work relied so heavily on the researchers who came before him, as all scientists do. He famously made this joke. He was mostly trying to insult his competitor Hooke, saying that he had stood on the shoulders of giants because Hooke was really short, and he was trying to insult Robert Hooke. But in this case, he really was. He was standing on the shoulders of about 1,000 years of Arab scientists who were translating and correcting the terrible work that the Greeks and Romans had done on color, because they really didn't understand, because it was early science. And so the many of the Arabs, over the course of from about the year 200 through about the year 1200, were experimentalists and trying to figure out fundamentally why light didn't just reflect off of things, but sometimes refracted in a way, it would go through something and bend, and how that changed the way that we perceived colors, looking at, for example, trying to figure out what a rainbow was and how colors changed in that range. When you look at a rainbow, why light could be one color and then another color, and how that related to the pigments that they were using every day as dyes and as paints. Because of course, human beings throughout human history have taken natural materials and turned them into the stuff that we could use to make give colors to surfaces, and that there is I think it's about 80,000 years old. The artifacts found in a cave called Blombos in South Africa. Basically, they found abalone shells with stones inside them that were used to grind ochre, iron oxide, the red earth you would see in South American desert or southwestern U.S. desert or on Mars, to turn that into a red pigment that you could decorate a person's body or a wall of a cave. So by the time Newton is doing the work that he is, he knows that there are these colors, this colored stuff that people make, and you can mix that stuff together, and it'll apparently have a different color. And he knows that that light shining through these new optical technologies called prisms will seemingly break into other colors that the light didn't have. So in 1665, he, in a way that all of us can unfortunately probably relate to now, is put on work from home from the university because of a pandemic. In his case, it was the plague. He goes to his mom's house, as so many people did. He turns a study upstairs into his office, as so many people did in the past year. And one of the experiments, and starts to play around with light and his own eyes. So he does stuff like sticks needles into his own eye to see if he can make himself see colors and light. He stares at the sun for too long, and that messes him up for a while. He has to stay in the dark room for a week until he feels better. But one of the experiments that he does is he shuts the shutters. He closes the room off to all the light of day, and then pokes a little hole in one of the shutters and gets one of these, he's been able to get hold of a good prism. Optical technology is just beginning. Folks like Galileo are using telescopes. He's working with these prisms, and he puts the prism in the way of the beam of white light that's coming in from outside of sunlight, and on the opposite wall, it breaks into a strip of multiple colors, into what he would have seen as a rainbow, and he names it the spectrum. And what he then learns is that if he's able to put another prism in the way of one of those colors, it doesn't break up any further. It stays that color. So something has happened. He's somehow bent light. And this is some math that he's able to figure out based on a lot of that Arab work and the work of others who came in the 12 and 1300s, that when you interrupt the direction that white light is going, something changes also about what color it is. He doesn't really know what.
Sorry to interject. You also tried to recreate that experiment.
I did. I was about to say it's a lot harder than I just made it sound. I bought a couple of. It's easy to get good quality prisms now. I tried to do it myself. It's really hard. It was really hard to do, especially the distance he was doing it. People don't realize it was about 20 feet that he had gotten to throw, because he really got a big spread of that initial spectrum. No, I couldn't do it at all. I could get the first one. I couldn't break it up into the second one. So clearly Isaac Newton is a better scientist than I am. I don't know that there was ever any question that was going to be the case or not. I tried. Didn't work. But I believe him. I believe that it worked. So why is that interesting? Well, what he's figured out is that in the whitish or yellowish sunlight that people perceive, that the colors that we see are somehow hidden there, and he wraps those into a circle, invents the color purple to join the violet at one end with the red at the other, and not invents the color, but uses the color purple as a name, says that's what connects the two, and sort of gives rise to the idea of a scientific and objective way to map colors into a space. Other people have been trying to do this for thousands of years, and he's got the first kind of mathematical version of that. And so that sets off many more researchers trying to figure out, well, how does the eye see those colors, and what are those colors made of? At about the same time that that's going on, you know, he's doing that in the late 1600s. By the time you get into the middle 1700s and the late 1700s, the kind of early industrial revolution, people are also trying to find more and more natural materials, synthetic ones, to make into new colors. And that's going to be the real hallmark of the later industrial revolution, and certainly in the 20th century, of an explosion in the materials that people can use to replicate the colors that they see in the natural world around them.
Can you talk to us about the development of some of those colors? For example, something as simple as white.
Right. The famous one, the one that everybody knows, is Perkins mauve. Was an accidentally developed this sort of pinkish color. But I actually got obsessed myself, and part of my journey to writing this book was I got really interested in the color white. And I got interested in the color white because of a particular pigment called titanium dioxide, which is a modern pigment. It was invented in the early 20th century. And it is ubiquitous in the human-built environment. Titanium dioxide is basically, if you look around the room that you're in right now, any surface that's artificially colored, that's colored by human hands, probably has.
And it's even in food, isn't it?
Yeah, it is. Because it's very bright and very opaque and very inert. So you'll find it in plastics and in paper and in paint and sometimes in the white on powdered donuts. It used to be in the filling of Oreo cookies. I don't think they use it there anymore. In cosmetics, it's all over the place. And I got really fascinated by why and how that should be. Well, titanium dioxide was a replacement. And in fact, for thousands of years before that, the color white, the white stuff, almost always was lead white, was made out of lead, and probably invented by the ancient Egyptians. Basically, you take lead, pure lead, and you kind of cook it in vinegar, and the vinegar, the acetic acid has a chemical reaction with the outside of the lead, and it produces this white powder. It does a lot of this. It's really useful. It's the way you make white paint and other paints. It's what you would see in almost every in pigments for thousands of years. It's also, as toxic as lead is. The lead paint thing was a true thing, and the people who made it would get very sick. The people who used it would get very sick. If you consume it, you get very sick. So everybody knew they needed a replacement.
Sorry to interrupt you. Really fascinating to discover from your book that we knew even in Roman times that this paint was bad for us. Yet we continued to use it.
Even Pliny, wrong about so much, but even Pliny in ancient Rome writes about, like, hey, maybe don't use lead as a vessel to mix your wine. There were warnings that women who were wearing lead paint cosmetics shouldn't wear them to the baths, to the spa at Bath, because there was sulfur in that water, and that sulfur interacts with lead and it turns black. So they would come out and their white makeup would have turned black and they would lose their hair. A lot of the pictures that you see of Queen Elizabeth, the kind of famous one where she's got the white pancake makeup and her bangs it looks like cut all the way back. The white makeup would make people lose their hair also. So that was probably a consequence of using too much lead white in her makeup. Benjamin Franklin wrote about how toxic lead was, and that the lead rooftops that they were using in the colonies were leaching lead from rainwater into the rainwater out of barrels that people were drinking. So people knew it was toxic, but there was no replacement, and there was a huge business in white paint. So in the early 20th century, when an engineer and metallurgist, chemist named Auguste Rossi, who was trying to figure out at Niagara Falls, at a lab in Niagara Falls, using the power of the electricity to do some chemistry on it, to try to figure out a titanium steel alloy to be stronger for rails. He really understood the metallurgy of titanium, element very common that had been discovered about 100 years previous. And he realized that as an intermediate step in the process he was trying to come up with, he had produced this bright white powder. And he knew that there was a need for a replacement pigment, that there was a huge market for this stuff. So he famously dipped his finger in some salad oil and then mixed it with the white pigment and brushed it across a piece of paper and realized that he had a new white. And this would become the defining white pigment of the 20th century. And starting about 1920, this was the thing that kind of changed the brightness of every color that people saw.
And they added, was it sulfuric acid to titanium?
Yeah, the process, the original process required sulfuric acid, which was dirty and gross and hard to do. There was a replacement process that was allowed for a pure version that requires chlorine gas, which is also highly toxic. I went to one of the facilities that makes this stuff today. It's an $18 billion a year business, and I went and there were giant pipes that were moving chlorine gas around. Chlorine gas is a highly you die. And what they said about the safety of it was that if you never want to see chlorine, like if you see it, you're dead. So they were like, and I think one of the guys I talked to said he had seen it once, like in some catastrophic thing where he'd seen this stuff. So it's an industrial gross process, but so are so many of the things that drive the Industrial Revolution.
And although titanium dioxide is still considered safe, the EU have put some things in place to ensure that labeling is detailed. Could you talk about that?
Yeah, it's like so many of the things when we talk about carcinogens, because that's what's at issue here. It's a complicated issue. There's some science, it's preliminary, that says that particularly titanium dioxide nanoparticles, which is to say particles that are smaller, that are on the scale of nanometers, not microns, which isn't really what's in the pigments. The pigments have some of that, but the pigments are mostly at the micron scale because the size of a pigment particle is really one of the things that gives it its color, among other features. That the nanoparticles might be, like other nanoparticles, carcinogenic. And so the EU has issued some warnings that say that about titanium dioxide broadly. But a lot of the studies are actually on inhalation of the powdered titanium dioxide, which isn't something that most people ever come into contact with. You come into contact with TiO2 mixed into a paint or embedded into a plastic or something. So you very rarely breathe in titanium dioxide dust. I'm not even sure where you would encounter it. And even if you do, it's not usually the nanoparticles, and it's not clear whether those mess up your lungs in an inhalation kind of way, or whether there's a lung cancer consequence. So the science there isn't finished. It needs to get done, and it's confounded by the fact that titanium dioxide is embedded in the industrial processes of so many different businesses that trying to get just the nanoscale particles out would be almost impossible. You'd have to remake entire supply chains, which you would want to do if the danger was great enough, obviously. So the business fights against that. The business interests fight against it, and different scientists are on different sides of this too. So it's still kind of a thing in play, as I understand.
And it doesn't just exist in its white physical state. It's also used to brighten up colors, isn't it?
Right. That's part of the thing that makes it so useful, is that you'll find it in a red paint or a blue paint or whatever, any shade as well, because what it does is it confers opacity and brightness. So brightness is the thing that makes, like, wow, the color really pops. There's a story, it might be, this might be apocryphal, but I like the story a lot, that in the days of the Cold War, there was more titanium dioxide available in the West than there was to Russia and the countries associated with the USSR. And so, like in Berlin, when it was a divided city, in the West, the colors of the paint were much brighter because they contained titanium dioxide. And so when you would go over the wall, there was it was kind of dingier and not as bright and not as beautiful. It might also be that they didn't have as much money, and so they weren't repainting as often. But you sort of got these more muted and more pasteled colors on the east side of the city. But so even now you'll find it not just for that brightness, but also opacity. It lets less light through, which means that you need less of it to cover a surface, for example. So it's much lighter. It'll be the main ingredient in a can. You buy a can of paint, most of that is just titanium dioxide, giving it the properties that people like about its paint. And you'll see it. You'll go back to your bathroom and look in your medicine cabinet and the shaving cream and the acetaminophen and paracetamol. All the like every pill, every capsule, every cream, every unguent will have titanium dioxide as an ingredient.
Can we talk of the whitest white on Earth and the laser technology that was used to try to find out why a beetle shell was so white?
I'm not even sure it counts as the whitest white anymore. I think they found another. I think they found another one. I think there was a paint I was reading about since the book came out. Yeah. But when I was writing, there's a particular kind of beetle. Beetles have these remarkable shells because of the structure of a material called chitin. Same stuff in lobster shells, and it because you can organize the shapes and layers of chitin in remarkable and specific ways. Instead of the pigment, the way we think about a pigment is a sort of a particle that would convey a certain color because of the way light reflects off of it. You can also organize structures that will actually be small enough so that they'll move, they will act like colors. You can have a structural color instead of a pigment. And beetle shells are a great example of this. So you can find beetles that look like gold and metal, or that are sort of iridescent, that flash different colors depending on what angle. And there's one called Siphochilus, I may be mispronouncing that, that has an extraordinarily bright white shell. And nobody really knew why until some researchers tried to figure it out. And the way they figured it out was they took pieces of the shell and mounted them on a little stand, and then shined lasers through them with sort of a screen around the pieces of shell, so that when the shell would diffract the laser, they could see shadows on the walls and try to understand how the material inside the shell was organized. And what it turns out is that in order to make a white, what you want are a very specific kind of lack of structure and lack of organization. So they're structured particles or materials, and then they're sort of at the right distance from each other, and those distances are different from particle to particle. And that's why and that holds true for things like milk, and for things like clouds, and for things like foam. All the stuff that you can think of that are kind of reference quality, objective white, all have that same sort of pattern of internal structural organization. And this beetle had it in like sort of the perfect amount to make this bright white, very reflective, very, very white shell. In fact, some researchers tried to then replicate that. They used an electrospinning process, which is actually the same process that's used to make the face masks, the surgical face masks or personal protective equipment that have gotten so familiar to people, where you have like two poles for electricity, you have a positive and a negative, and you kind of extrude this material with the exact right distance between the poles on a spinning drum. And when it would come out, it would organize itself, this material, a polymer, basically a plastic, would organize itself just like the beetle shell did. And they got the same kind of white, which could have potential uses for fabric or textile at some point in the future. I don't think they've really commercialized the process yet.
We've spoken about perceiving color through the eyes. Could you talk about the halobacteria that perceives color although it has no eyes?
It's a complicated question, because we get very used to the idea that, like, oh well, we have eyes, and so therefore we see colors. But of course, different animals with eyes see colors very differently than we do. I think I can think of example after example, but the classic ones are, for example, a honeybee has eyes that are built sort of differently than ours, but they have many of the same kind of photoreceptors, but they're tuned to a almost entirely different set of colors. So where we might see the broadly argued red, green, blue, the honeybee will see sort of green, blue, ultraviolet, and looks out at a world that is the same world that we see, because their eyes are pretty good, and sees it as a whole different set of colors, a remarkable set of colors. You can kind of get a hint of it if you look at flowers at kind of the end of the day when the sun is low and they look sort of luminous and incredibly beautiful in the magic hour, as a filmmaker or cinematographer might say. You're getting a little bit more of the ultraviolet there. And that's what the honeybee lives in every day, or the mantis shrimp with 12 different photoreceptors in its eyes instead of just the 3 that we have for color, sees a whole different world than we do. Well, that's even true of microorganisms that don't have eyes at all. I mean, how could they, right? The microorganisms are really teeny tiny, but halobacteria, which are they're not bacteria, they're from a whole different whole different kingdom on the tree of life than we are the plants, called archaea, or archaeobacteria. They predate human life. They predate all of their life on Earth by millions of years. And they still exist today. They're often what are called extremophiles, so they live in environments that other things can't live in, like super salty or super hot or super cold. These ones, halo is a prefix that means salt. They live in these really, really salt, like salt ponds or the briniest, briniest pools, whatever. And they're able to, they swim toward orangish light and away from bluish light. Or I may have that reversed. And so the question is like, well, how do they do that and why? Like, they don't have eyes. They don't need to pick out ripe fruit against the background of trees. Like, what's the point of that? And how do they do it's even more important, because you think, well, what are the receptors? What are the molecules they're using that photons are interacting with somehow and changing their behaviors? So what's probably true is that the bright light suggests to them open water, and so they want to avoid that because they can get preyed upon. Something else will try to eat them. And darker light means that they might be able to find food, or they can hide. So, okay, it's another evolutionary just so story. Nobody can interview halobacteria and ask them what they think. But the actual photoreceptor, the molecule that they use to do that interacts with photons of different energy levels or different wavelengths of light, which is a physicist, two ways of talking about the same thing in physics, in many respects looks exactly like the ones that are in the back of our eyeballs. It's a protein that sits on the inside and outside of a cell. It crosses the cell membrane 7 times, and it makes a sort of cage, and it has another bit of itself called a chromophore inside it. And the way that you shape that protein can change the amount of energy that it takes for the chromophore bit inside to go from being dogleg shaped to being straight. And so depending on how much energy it takes, that's how much photons can come into it, how many of the photons can come into it, or what wavelength can come in and change that. And that triggers a whole set of other cellular signals that then are the way that modifies the halobacteria's behavior, either, yes, go that way, or no, go the other way. And then for us, lets us develop a picture of color in our brains. And the photoreceptor in our eye looks the exact same way. It's this 7 transmembrane protein with a chromophore in the middle. So the question you would ask then is, well, did ours evolve from theirs? Is the way that we see colors, billions of years old on Earth? And one answer would be, well, yeah, obviously it is. It's the same. The molecules are structured the same way. That's clearly the way that living things can perceive different wavelengths of light, or photons of different energies. But the weird thing is that the halobacteria, the amino acids that make up that protein, the individual building blocks of the protein, are different than ours. The shape of the protein is the same, but it's like, I think I say this in the book, it's like building the same spaceship with different Legos. So you get the same shape, or making the same cake with different ingredients, I guess. You get the same, roughly the same end product, but with different building blocks. So maybe ours evolved from theirs. Maybe the living things that we know on Earth have evolved their color receptors from that. Or maybe there's just one really good way to perceive color that evolution just sort of figures out the solution to again and again. It does it once, stops there, starts again, and then figures out how to perceive color again, because it's just so useful to be able to perceive different wavelengths of light in the world around us.
And it converts what it perceives into, if I remember correctly, energy and information.
Right. Well, so then the question is, well, what's the halobacteria actually doing? And in studying them over decades, the initial idea was, well, they must have a pigment in their eye. That's what a photoreceptor is, essentially a pigment. It reflects some light and absorbs others, and the absorption of that light is what starts the cellular signal. But it turned out that what they were doing were actually they were using those photoreceptors that I mentioned. Some of them they're using, the first ones they discovered, not to regulate that behavior, to see light. They're not really seeing because they don't have eyes, but you get what I mean. But to for nutrition, to get energy. That they were doing almost a kind of early version of photosynthesis as a proton pump, moving energy through their cells. And that in fact they had whole other pigments that they were using to do the behavioral stuff, to move toward or away from different kinds of light. They were using it, and the parallel that I tried to make was they were first using it for energy and then using it to get information about their environment. So plants use light for energy as well. We use it for information, but it's this kind of interesting, to me, a progression progression suggests there's some final evolutionary goal here, and of course there isn't. But it suggests all of the different uses and meanings of light and color, that it's both information and power.
Can we just go briefly back to humans? Of course, we perceive colour through our eyes, but there was a fairly recent experiment where neuroscientists delved into the human brain and were able to make that person see colour. Can you talk about that?
Yeah, there's not a lot of work in this area, but of course there's a great deal of interest in what are now called brain-computer interfaces, or BCIs. This idea that you can take an array of electrodes in some form and attach it directly to a person's brain. You probably wondered about here, because this is where the visual cortex is, and then pick up the electrochemical signals that the brain what the brain does when it's at work, and then translate those signals into what the brain is thinking, and then get those signals into a computer and get the computer to do something. And you'd like that to be a two-way, an input and an output. So use it to control a computer as an interface, or control a prosthetic, or even talk directly to another person who had a similar implant. And then also to try to put information in, to say like, oh, I need to remember my address book. Instead of looking at my phone, I can have it zap directly into my brain, I suppose, or something like that. This is really hard to do, not least because nobody really understands what the brain is doing. Nobody really knows how brain. There's a lot of good ideas about how the brain works, but nobody really can say like, oh, well, we get an individual electrical zap, a change in an action potential along a neuron, talking to other neurons, sending chemicals to the other neurons to tell them to do the same thing or a different thing, and what that translates to in terms of a thought. But over the years, there have been opportunities to attach these panels of electrodes to human minds, to human brains, and try to figure out what's going on in that brain. Usually you would do that because you're trying to do some sort of medical procedure. Obviously, this is a big deal. It's brain surgery. You're putting electrodes on top of a brain. Most of this work is in non-human primates or in other kinds of animals. But there was a paper published out of Baylor University in Texas more than a decade ago now, where neurosurgeons were working with a person who had a very bad seizure disorder. And a seizure is the electricity in the brain not being controlled. It sort of starts to operate at random, and that can cause all kinds of problems. So they were going to try to find the part of the brain that was having that was causing those seizures, having that uncontrolled activity, and do something to it, probably try to take it out. Surgery. But first you have to find it. And the way you find it was you'd put this panel of electrodes. At the time, I think they just had 64 electrodes that you would stick into the brain and then wait for the signal to show up. But as long as you're in there, that makes it sound more casual than I mean it to, but as long as you're in there, you might try some stuff. And so they got interested in trying to figure out what happened when a person sees colors, and then to try to reproduce that signal and put it back in. So the first thing they did was they showed the person a lot of black and white and color images and just tried to trace what the electrodes would show. And found, like, when they showed pictures of the Lone Ranger, the cowboy hero, the Lone Ranger with the mask, which aired on television as a black and white TV show and then as a color TV show. So they showed pictures in black and white and then showed pictures in color, and the person's brain sort of lights up at the blue of the Lone Ranger's shirt. Turns out the Lone Ranger was blue, not just gray. But then they tried this thing where they put in signals as well. And the person, because the person was awake for this, could say what they were seeing while it was going on. The person reported being able to see, first of all, what are called phosphenes, the little flashes of light, like when a cartoon character gets hit on the head and the stars go around there, because you see those little flashes of light in your eye. Those are called phosphenes. But also they reported seeing the person described it as the blue that you would see as the spark if you put tinfoil into a microwave oven. You'd see that electric blue sparks. He saw that color. They were able to induce not just phosphines, but a specific color in the brain. And they don't really know, why that color and not another one, but it does give a hint, at least, of what of a brain-computer interface that could convey images. That you could put in some, if you had a sophisticated enough set of electrodes and understood enough about the brain and enough about how to put in signals, that you could actually induce colors in specific shapes, which is really all we're ever seeing, is color and shape with some dimensionality back, forward. And if you could induce enough of that, you could actually maybe induce images. That's what it sort of presages. That's a long way off. There's a lot to figure out until then. But I'm still struck also by the fact, it's interesting to me how much of color research runs up against rocky shoals when it tries to think about or deal with the colors blue and green. The GRU region of the spectrum are really troubling for the human eye and the human brain for a lot of different reasons. But of course, it would have to be just as David Hume had written in the 1700s, I guess, about the missing shade of blue. Here were these neuroscientists in the late 20th century, early 21st, introducing a new shade of blue that the person had never seen before directly into a human being's brain. I like the parallelism.
Can we talk about exponential technology and how that is advancing both our understanding of colour and helping us to produce new colours? Maybe beginning with Michael Foshey's work at MIT.
Oh yeah, Foshey and Shi at MIT and I want to make sure they both get credit because they're both working on the project together. They were trying to make three-dimensional objects with color was where this started. So using a color 3D printer to try to reproduce chromatically complex surfaces like wood, let's say, which has a bunch of different colors all wrapped up with each other and different ways of interacting with light, the specular color, reflective, sheen coming off the surface. And what they hit upon was an experiment to try to basically forge paintings, and not for crime reasons, but that they wanted to try to make reproductions of like posters, a poster for a painting that you'd put up in your dorm room at school. And specifically, they wanted it to have that property of color constancy that I was talking about earlier with the dress, where they wanted it to change under different colors of light the same way that the original would change. So one way that you can tell something is a copy, if you get a poster, that poster of Gustav Klimt's The Kiss that every college kid used to put up in their dorm room, you would know that it wasn't the original Klimt, because if you shined red light on the original Klimt, it would look one way, and if you shine the same red light on your poster, it would look another way. And like, obviously that's the poster. So they wanted to see if they could use this 3D printing technology to create replicas, reproductions of paintings that would react the same way under different colors of light, that would do color constancy the same way. And the idea would be that you could learn something about color constancy and also about 3D printing. And so they built this very sophisticated machine learning algorithm where they would show their 3D printer, the computer that controlled their 3D printer, a bunch of different colors on a tiny little chip, and tell it to go through its entire array of possible pigments that it could print with until it could reproduce that color under different kinds of light. They would show it that color under different lighting. And in order to do it, they had to create their own sort of custom-built 3D printer. Most reproductions of color, if you're thinking about a magazine page, let's say, there used to be printed magazines, use 4 colors of ink, 4 primary colors. They call them CMYK, but that's cyan, magenta, yellow, and the K is for black. The white is usually the white of the paper that it's printed on. And when those are for reflective surfaces, those are called subtractive colors. When they overlap, they create all the other colors that you might be able to see. A screen, like the one you're looking at me on right now, and I'm looking at you on right now, tends to use 3 different LEDs for each pixel that it generates, a red one, a green one, and a blue one, and then it might have white as well, same way that the same colors that the eye perceives. All of these are much more focused wavelengths, and then the amount of each of those as they overlap creates all the colors. So for the primaries that the 3D printer these guys used, they had a red, green, and blue, a black, a white, because there was no paper substrate. It was a titanium white, in fact. They had a cyan, magenta, yellow. I think they had an orange and a purple. They ended up with like 12, if I remember right. They ended up with like 12 primaries. And the computer, using those having access to those primaries, was able to print 3-dimensional. They were still printing a flat thing, but basically they were able to print things that were under every color of light, all but indistinguishable from an original. One of their advisors had a partner who was a painter, so they were using that person's paintings as the original, the substrate, I guess. But the thing that fascinated me about that is that there's a set of equations called the Kubelka-Munck equations. They're differential equations that approximate very close to perfectly, but not perfectly, the way light moves through layers, through very, very thin surfaces. Essentially, this is a calculus of light, because it divides a surface into infinitesimals, basically, and then does the integration through those to say this is what color that's going to show. And it's really important for things like car paint and for house paint, and for understanding how color and the physics of light work. The Kubelka-Munck equations are some of the fundamental things that they teach, engineers and color scientists, but they're not perfect. And here, and one of the things they don't do that great is like figuring out color constancy. So I asked these researchers, I asked Shi and Foshey, I said, like, well, so your computer has a different solution for Kubelka-Munck, right? I mean, your computer's figured this out. Did you ask it? You have some real fundamental science here. And they said, no, we don't really. Not only do we not care, they said, but because it's a machine learning algorithm, it's all but a black box. There's not really any way to ask it to say, can you give us the new solutions to the Kubelka-Munck equations? This is great. We can take this to some paint company and have better. They're like, no, we don't really know. So for them, the thing that really struck me about this was that their computer knows something about color that no human knows. Some fundamental truth about the science of color that no human scientist knows, and it just can't tell us because we have no way of asking it.
As we reach out further into space to, as humans, discover more about ourselves and our planet and who we are, this pushes out the envelope in as far as our understanding of colour and application of colour. How do you think, I mean, you mentioned in your book the adaptations to the camera on the Mars rover. How do you think the science of colour is going to evolve with more complex exploration of space?
Well, there's not that much of this in the book, but I have a couple of things that I've been sort of chewing on about this. Recently, NASA sent to the International Space Station a very powerful digital camera from a company called Red. This isn't helpful for this conversation because I say it's a red camera and everybody thinks, oh, the camera was colored red. The company's called Red. They sent this amazing digital camera called the Red camera. This is the sort of really, really high resolution, wide color gamut sort of camera that filmmakers will use, movie makers. And the astronauts would take this camera into the cupola on the space station, which is where they have all these windows and they can look down, I suppose, is space, so it's hard to say, but down at the Earth, and they would take pictures of it, and then the astronauts would complain afterwards that when they look at the pictures on any screen that they could get or printed out, that they didn't see all the same blues and greens that you could see when you look down at the planet. And that's because the screens that we have, while new ones are very, very good, 8K, UHD, wide color gamut screens, they still aren't capable of showing all of the colors that the human eye is able to perceive when you look out a window. And so there are researchers, engineers now, and cinematographers working on screens that have more primary colors in the LEDs, for example. So they're able to show more of the colors that you see out in the world. So I think that's sort of in the intermediate term, as we spend more and more time sitting in front of screens and consuming sort of color information from screens, that they'll be able to show more of the colors and more of the dynamic range, the brightnesses from black to white that are proxies in our own minds for emotional content, that tell us how to feel about things because of what we're seeing. And then well beyond that, already there are researchers who study exoplanets, planets outside our solar system, who use color to get information about those worlds. So, for example, you can tell from the spectra that an exoplanet emits what is in the atmosphere of those worlds. And maybe if you got a clear enough view, whether there were plants or some analog to plants on those worlds, because chlorophyll on Earth has a very specific emission spectrum. So you can see especially from the infrared, there's something called the red edge. You can see, because they're green, they're absorbing a lot of red, right? They're reflecting the green, but they also drop off at a very particular wavelength, and you can see that, where there's plant coverage on Earth. You can do that same thing with exoplanets. You can figure out, well, are there plants up there? But the thing that I love about this is that what we think of as color and what humans and all life on Earth that's ever lived on Earth is evolved under a very specific emission spectrum, the way that our sun emits light. And we tend to think of the sun, because it's a sort of white yellow sun, our star, as emitting all of the wavelengths across the electromagnetic spectrum evenly. But it actually doesn't. There's some wavelengths that it emits less of than others. And another star, a different star, would have a whole different emission spectrum. So a planet that existed under that star at a different distance, because that makes a difference too, would have an entirely different baseline kind of light. Color would be a different phenomenon on that planet. And the way, if a human being could ever go there, which is probably impossible, honestly, but if a human being could ever go there, the way that we would experience color on that planet would be biased by the way our eyes evolved under the color that we experience here. So anything that lived on that other planet would have evolved to see color the way it exists there, and would literally see a different world than we would see. You could also imagine color having a whole different meaning there, having a whole different use. So on Earth, plants typically absorb just about all of the visible light that human beings see, except for the green, which they bounce back to us and we see them as green. But maybe you could think of you can imagine a different kind of absorbing pigment that absorbed all of the light. So the plants could be black, or maybe they would absorb all of the light, but would also be more specular somehow. So they would be like reflective black. It'd be like, that'd be the most metal plant. Or maybe they'd be purple. They would have some other reflective peak, whatever they emitted. There's a planetary system called Gliese that's sort of within striking distance of the Earth. I can't remember how many light years away it is, but it's a potential journey if we had the right rocket. And there are a few planets around that star that are rocky like Earth, and that are the right size and the right distance, that you would think are very promising for the kind of place that could have the sort of life like we have on Earth. But the thing about the Gliese system is that star periodically emits huge gouts of ultraviolet. And ultraviolet's really bad for living things on Earth, unless you have the right kind of biology to deal with it. It's the thing that gives you everything from a terrible sunburn to cancer. So we would tend to think of a star that emitted regularly huge blasts of ultraviolet as essentially being sterilizing, that there would be no life there. But you could imagine a biology that had the right kind of replicative machinery in a cell to recover from errors introduced by ionizing radiation, or the right kind of pigment on skin, like could change color like an octopus or a squid does, to armor up against ultraviolet, when it happened. And for that kind of life in a system like Gliese, maybe periodically what they see is just fireworks. Maybe they see periodically a beautiful light show where every living thing kind of lights up under ultraviolet for a period of time when the star emits these sweeping things that make it possible for life to exist on those worlds. And that's an entirely different, colorful universe that requires different kinds of eyes and different kinds of brains and different kinds of physiologies, all of the things that make it possible for us to perceive the colored universe around us.
Before we go, is there anything else that you would like to add that we have missed from this wonderful book?
I think we pretty much ran through it. I guess I would say that what I hope that, to the extent that it has a single takeaway, what I hope that it is that color is this amazing interaction between the world that exists outside our heads and the world that exists inside our heads. And to me, that in as much as color has also been a thing that has driven economies and historical change and the desires of human beings to change their environment, all the things that technology is really about, that it also is a way for us to understand the places where our selves, our minds, are affected by and then impact the world that we live in and move through all the time.
Adam Rogers, thank you very much for your time. It's been an absolute pleasure talking to you.
Thank you for having me. I really appreciate it.
Thank you very much for being with us on this episode of the ideaXme show. Our mission is to move the human story forward by sharing knowledge of the future. You can find us across the internet on all the major audio podcasting networks at www.radioideaXme.com, YouTube and Vimeo. Please subscribe